Hi, everyone. Thank you for joining me. My name is John Francis, and I'm the Vice President of Business Development and Marketing here at ETAP. And today, we're going to learn and discuss how utility engineers use ETAP's transmission and distribution system analysis and optimization solutions to optimize capacity planning, improve reliability and safety using either schematic or GIS geospatial views. We will start by reviewing the grid's top priorities, the ETAP Digital Twin Foundation, how to apply unlimited scenarios through the multidimensional database, engineering network analysis applications provided, and using these solutions to optimize transmission and distribution systems. And at the end, we will conclude with questions and answers. What are utilities' top priorities when modernizing the grid? Utilities have taken on a greater leadership role in sustainability. The incorporation of renewable generation technology has ushered in a new wave of green power. This brought forth grid code requirements to ensure quality of service while increasing resiliency and reliability. Improving financial performance and energy efficiency is always and will continue to be a goal, as is prioritizing safety above all else. And this includes safety for their employees, equipment, and the public at large. Now, let's discover how engineers are leveraging the ETAP Digital Twin as the foundation for their grid modernization program to design, operate, and automate smart grids. The Electric Digital Twin platform provides a single source of truth solution with intelligent modeling views and core capabilities to create, configure, customize, and manage your electrical power system. The intelligent single line diagram. It's a multi-layered one-line view of the digital twin. It includes functionality and awareness of the device's characteristics and system behavior. The GIS ETAP Geospatial Network Diagram offers a user-friendly environment for creating, visualizing, and managing the geospatial network database with built-in capability to directly import electrical data from your GIS database. The GIS database then dynamically creates an equivalent single-line diagram, feeder view, and network view. During this presentation, we will focus on the analysis and optimization of electrical networks within our one-line and GIS views. Many of our customers do continue their digital twin journey from design to operation, adding web-based SCADA HMIs or local SCADA systems, alarm screens to their operation teams. For an integrated solution, this provides a unique 360-degree network view, allowing the engineering team to efficiently, optimally design and expand the network using their operation knowledge while empowering operators to dispatch the electrical system with design knowledge. When a GIS database is imported into ETAP, users have the ability to display the networks as geospatial views, substation views, feeder views, and most importantly, all three are centralized to a single database. Similar concept to having multiple one-line diagram presentations to the single database for many of our existing users who use ETAP for the one-line. Very similar concept. Now you can easily take a variety of formats and import the data in an ongoing incremental update with either schedules or on demand. Many formats are accepted by ETAP, including SIM, which is a common data model language for information exchange in the electric utility industry, supporting IEC 61970 and IEC 61968 standards. Multispeak, which is a specification standard that defines standardized interfaces between software applications, which is traditionally used by the rural electric co-op industry. Specific third-party software such as Esri ArcGIS, GE Small World, Hexagon, and others, as well as Excel or XML and KML format. ETAP's unique multidimensional database provides the ability for engineers to analyze an unlimited amount of scenarios, what-if conditions, essentially. And these include graphical visualizations, which we discussed the one line in the GIS, We also have specific views for protection, safety calculations, cable layouts, data revisions, which includes ratings, properties. You can have a data revision layer specific for real-time information, settings, recommendations. If you're working with a consultant, they can provide you a recommendation, and that can sit isolated as its own layer as to not override your base model. And configurations, including protected devices, switches, really managing how your system is operating. So all the operational conditions of your system can be combined into unlimited scenarios, incorporating these presentations, configurations, and data revisions, as well as applying time series. So when you get into renewable energy assessment or any type of capacity planning in the future, changes in generation or loading, the time series can be implemented and adjusted again to create another facet of the scenario. And there is no limit to the amount of scenarios that can be handled. When your scenarios are completed and defined, you can use project macros to run multiple studies at the same time with a single click and generate multiple reports instead of running each one individually. Overall, ETAP has over 150 solutions to choose from. Here, we're summarizing the solutions specific to transmission and distribution and for engineering and design calculations only. Operation, definitely there are many more solutions to choose from for the operation team, but for this presentation, we're focused on the design, engineering, analysis, and optimization. Those modules include load flow, short circuit, arc flash protection and coordination, overcurrent, overload, and distance protection, power quality, stability calculations, and then optimization engines for switching optimization, volt bar optimization, optimal power flow. Now, of course, we don't have time to go through each one individually, but please contact us at any time and we'll be happy to present any of your selected applications and solutions required for your project. I'm working on a project with solar, renewable energy, and battery energy storage, wind. Now, essentially, in our unbalanced load flow calculations, I can calculate the AC and DC system together. So with my unbalanced power flow engine, I see all my DC results and all my AC results in the same solution. You don't have to run each one twice. You can dictate which results you want to display on the one-line diagram. In this case, I'm showing current and voltage, but you can show real power, reactive power, frequency. Any of the results you need from a load flow study can be displayed. Beyond running system analysis and transmission and distribution network applications, powerful system optimization solutions help minimize operating costs and maximize performance while increasing the value of the energy investment. ETAP optimization solutions help engineers define strategies to save in energy consumption, reduce greenhouse emissions, increase reliability and resiliency. And on the next example, let's look at how to use ETAP optimal power flow to minimize fuel costs in a transmission system. The transmission model includes the generation units and interconnections to other grids. The power necessary is dependent on the loading of the system and the interconnection requirements. ETAP provides the tools to determine the generation dispatch based on different objectives. Opening the study case editor allows us to define the objectives for this project. These objectives can include minimizing losses, minimizing cost of generation, optimizing voltage and flow, in addition to many other requirements. You can optimally dispatch the generation units based on single or combination. This is done here in the Objective tab. For this project, let's use fuel cost. In addition, I can indicate to the program which generators are available for dispatch. This is done in the generator megawatt page. And one more item to consider is we dispatch the proper reactive power to maintain the voltage within acceptable limits. Once I've set up the study case editor, I can look at the generation costs of the generators. Let's look at Gen 6 and Genset A's fuel cost. Using Control Find, I can locate Gen 6, and I see the fuel cost through the cost function coefficient. This is set to 22. Now within the editor, I can look at Genset A and see the comparison at 18. So when we run the optimal power flow calculations, which is done in seconds, we can view the results on the one-line diagram or into the reports. So on the right-hand toolbar, in the study mode toolbar, we can run optimal power flow. And we see the results including real power, reactive power, current, frequency throughout the entire transmission system. These results are displayed inside the composite networks all the way through across the entire network. From the main model to each composite network, we can view the results. We also can print the reports. I'm going to select the optimal settings results that were calculated from within our objectives. These reports will show the optimal dispatch. The voltages are within the acceptable limits, so the reactive dispatch has passed. The real power dispatch can also be seen. We can see the increase in megawatts of genset A, being a more cost-effective unit in comparison to Gen 6. Thus, Gen 6 is being reduced since it is the less efficient generator. Our next objective is to minimize VAR losses and improve the distribution grid efficiency by optimally managing system-wide voltage levels and reactive power flow. So initially, I'm running the unbalanced load flow module, selecting the feeders incorporated, and running my steady state calculation. Now this is done on a GIS view. Previously, we were on a one-line view. Now, transmission and distribution can be modeled in the same project file. But for this example, I am running a distribution system, as you can see across this Google Maps. We see it's color-coded by feeder. So each feeder is identified by the color and the connectivity. Zooming into the network, I can now clearly see the results that were calculated from my unbalanced load flow calculation. Here, I'm showing real power and reactive power and voltage. Essentially, I can show this per phase or an average of 3 phases. In this instance, I'm showing the average of 3 phases, but I can very easily select to display the results per phase. Now, to improve my losses, I'm going to the volt-var optimization study case. I'm defining my objective, which is conservation voltage reduction, ultimately peak shaving. Once my objective is defined, the system is now going to calculate the optimal settings for load tap changers, voltage regulators, switching capacitors, any of the equipment defined within the study case editor. So in this example, I am selecting to include the first five transformers, which are T4, T9, T5, T7, and T6, as shown in the study case editor. Their operating conditions are shown. Same as the switching capacitor. So I have 2 capacitors in this project. Both are selected to be included. And again, operating conditions are shown in the study case editor. From there, I can simply run volt-var optimization calculation. And as you can see, the power flow results are shown on the GIS, including the direction of the real and reactive power flows. Within my volt-var viewer on the bottom of the screen, I have my losses, and the improvement is clearly identified. And now I can see the differences for each feeder of the peak shaving from my initial power to my final power and the difference, and then the details of the changes within each equipment. So the tap setting changes and the capacitance changes from all my included voltage regulating equipment. Let's run one more project to optimize voltage levels and balance our feeders. And essentially, we're going to run an unbalanced load flow to get our steady state results, as we did previously, again on a GIS network. So we run unbalanced load flow to find our steady state results and see the operating as is conditions of the system. Now we can view those results. Last time we viewed them on the GIS. This time let's look at the feeder summary from our output report. And this feeder summary will give us an easy to identify report for our losses, so we can clearly see the losses at each substation down the feeder per phase. So now we know the areas we need to improve upon. And we're going to improve from our switching configuration. So in our switching optimization module, I'll open the study case and define my objectives. I'm going to select multiple objectives for this calculation, including minimize losses, feeder balancing, and optimize voltage. So the software is going to have to balance the results between all 3 objectives. You can change the weighting factor if you like, so one becomes a priority over the other, or you can keep them all the same. The second thing we will have to define, I'll keep as is the categories for loading and generation. I'll keep them at design level. The switching groups, we will keep all active feeders as identified and include them all in the project so we can clearly see the active feeder IDs and the color per feeder, and then decide which switching devices we want to incorporate in the solution. All the current statuses are displayed, all the groups are displayed, and the voltage levels, and then how we want to alert any of the results we receive. All this is defined in the study case, so now it's time to run the study. As we did before, we click on Run Switching Optimization on the study mode toolbar, and we'll receive our results quickly. The Switching Optimization Viewer is located within the System Manager, so here we can clearly see the gains at each level and at each feeder, and then the actions that were defined. So within our losses, we see the improvements, and then the actions tab, we see there were 8 actions. We see what they were before, the initial conditions grayed out, as well as the final configuration. The final and very important solution that I want to discuss today is reliability assessment. The reliability indices are normally used to predict and assess the reliability of a distribution system, consisting of 3 indices, typically that are load point average failure rate, average outage duration, and annual unavailability. Within the ETAP editor of any device, you can go to the Reliability tab and select from the library IEEE 493. Reliability data is provided in our library. So you can select that and you see the parameters that are updated for the transformer. And in this case, I'm showing the load, and you can specify the sector for this particular load. And then I open the study case editor so we can select the method, whether it's a single contingency reliability assessment or a double contingency assessment, the maximum momentary duration, and which devices I want to plot when calculating my results. So I can specify the specific buses and any other equipment I'd like to create a plot for. Now, once we run through our study mode toolbar, we run the reliability assessment, we see our results on the one-line diagram. The results are shown or dictated by your display options. So in this case, I can switch from average failure rate to expected energy not supplied, and the results are updated on the one-line diagram at each location. It's very easy. I can select each one. We have many different indices we can calculate from. If I want to show the momentary index, I simply change it again on the display option, and now I see the momentary indices results at every location. Or I can select our output report results and see them all together in one output report. So all the typical indices that are required for distribution reliability assessment are included, including SAFE, SAIDI, KD. We talked about, you can also calculate the expected energy not supplied, expected interruption cost, interrupted energy assessment rate. This is shown per device, the sensitivity analysis for expected energy not supplied. Here's the plot for expected energy cost. So you can see T2, T22, T23, each ID is signified on the x-axis. It's the element cost and the result on the y-axis. And again, we can see this on the one line or the GIS view. In the other examples, we were either on the one line or GIS, but they are in sync, and any calculation study can be run on either view, and you can assess them on the one line or the GIS system. Using our optimization solutions, we were quickly able to perform 3 project samples. One was to minimize fuel cost on a transmission system. The next one was to reduce voltage and perform peak shaving to optimize capacity planning in the future. And then finally, we looked at the switching optimization solution to minimize losses and balance our feeders. Now, there's many more engineering and optimization solutions provided by ETAP. But I want to show 3 of the main ones for transmission and distribution projects. Again, we have over 50 engines specifically for design and engineering on an integrated platform with many intelligent time-saving capabilities to streamline project execution. We didn't talk about this, but for all the projects, we have cloud access for collaborative project execution with automatic error corrections. So using ETAP Net PM, you were able to synchronize between multiple individuals working on the same project for cloud access and collaborative project execution. And we were able to solve some of these massive projects extremely efficiently and quickly using a modern multi-core unified solver. And this was solving AC and DC networks together. If you were to perform many of our other solutions, including protection and coordination, we have many automated rule-based applications. So we were looking at some of the objectives that were clearly defined. In addition to those objectives, you can set rules. And when you run your system analysis, if rules are exceeded, it'll automatically alert you and provide suggestions on different settings and outputs to perform to stay within your rules. Within our GIS database, there's an equipment warehouse generation for optimized database performance and improved interoperability. So it's not just the library files. You can create a warehouse that hosts asset information and helps as an asset management solution within your GIS database. We talked about easy scenario definition using our multi-dimensional database where you can apply different revisions for electrical data, configurations for switching statuses, loading conditions, generation categories, mix, match, and define, and ultimately define unlimited scenarios which can be run with a click of a button using a project wizard. And we saw the switching optimization and volt-bar optimization result analyzers. Many of our engines have powerful study result analyzers to compare multiple scenarios immediately. You can select to apply worst case and best case conditions. And ultimately, trusting these values is extremely critical. All of ETAP is designed and developed under our nuclear QA program, assuring engineering accuracy calculation, library assessment, validation, and verification, so to assure that all results are trusted through a robust verification and validation process. And with that, thank you all for attending. Thank you so much for joining me during this presentation.